All right, welcome back to the lecture series I now call, wait, what? Or, Kevin, would you slow down?
Yes.
So to start with, Vin had a question.
So my question is magnetic field
Yes,
about counter EMF.
counter EMF.
Yeah.
All right. Just to explain it a little bit more.
Yeah.
I don't know if I can explain it any better than kind of what I've done, but I'll redo it, maybe slower and louder. So as this electrical charge, we'll just make simple words, comes rushing into any sort of windings, turns, a coil as it is, it starts to build up this magnetic field around it. So it becomes each wire becomes its own little electromagnet. All right? So as that electromagnet starts to expand, well, what's right next to it? Another wire, and another wire.
Electricity when it expands like
Well, it does, and it goes back to where we started, where whenever you have relative movement between a wire and a magnet, which is what we have, relative movement. In this case, the wire stays still, the magnet moves. So we have this magnet moving across this wire, which is going to create electricity. But it doesn't create it in the direction that pushes it into the coil, it pushes it out of the coil the wrong way. So as it starts to build up, this electricity builds up and stops it. But it only does it for a period of time because this field is slowly growing because we're looking at a waveform, so it's growing. Then it gets all the way built up and it's gone, right? It just takes this 5 time constants that we talked about to build up, and now it's fine. But then what happens is the current starts to fall off again. Well, now we have a change. It starts to collapse. That's, again, a magnetic field moving across wires. So that collapse is going to, or the collapse, creates relative movement, which creates current flow. But the current flow is in the wrong direction. So the current's trying to go back out that way. Now it comes over here and goes, nope. Everybody just wait. Stay where you are. But it runs over it like a I was thinking of just a cartoon where a guy tries to stop everybody and then run over him, kind of a thing. So hopefully that helps because it's about the best I could do. All right, so we were talking about inductive reactance. And what was inductive reactance again?
Opposition, opposing.
We can use just regular words and terms.
current changes constantly.
No, we're talking about inductive reactance. So I say, well, it's just got a lot of inductive reactance. Well, what is that?
Proportional to the inductance and frequency.
Well, that's what.
It's like resistance.
There. It's like resistance. Like resistance in a coil. So you can have a coil in a series, you can have it in a parallel, but it's all about the coil. That's all we really talked about yesterday was coils. And do coils have resistance? Like if I want to measure it with an ohm meter?
No.
Not really. It's just wire that's wound. And so there is no resistance. But then I hook it up inside of an AC circuit, and what happens? We have that counter EMF thing, all that. So it wants to. So here I have something that's trying to block the flow of electrons. Well, what is that? Well, it's like resistance. So it's like resistance. It's counter EMF, and that's like resistance. So here we're going to end up with this problem where we measure it and go, no resistance. Plug in the circuit, and you'll be like, what the heck's going on? There's like all this resistance. Well, there is. But we don't call it resistance because resistance belongs to resistors. We call it inductive reactance. So inductive reactance, again, is expressed as X of L. We wrote that yesterday, represented X of L. And it is proportional to the inductance, which means if the henries goes up, so does the X of L. So if I have one coil that has 1 Henry, coil that has 2 Henries, this one with the 2 Henries is going to have more inductive reactance. And all of that Henries, where does that come from, is the core and the material and the wire size and a whole bunch of other things. And then we said also that it is proportional to the inductance and also the frequency. So there's the frequency and there's the inductance right there. So if the frequency goes up or the Henry's goes up, you get more inductive reactance. Okay, and the formula is X of L equals 2 pi FL, where X of L equals inductive reactance and we're going to express it as ohms. So I would say like X of L is 5 ohms or something like that. F equals the frequency, which we already talked about. Well, you know what pi is, you know what 2 is. So 2 represents 1 more than 1. Pi is 3.14. Frequency, and L is inductance. How much the inductance is. So as an example, determine the inductive reactance. What is the X of L? What is my X of L? If the frequency is 60 hertz and the coil or the inductance is 7 henries. What's my inductive reactance? 2,638. 0.94. Okay, if you say so. So X of L equals 2 pi times 60 times 7. So I didn't bring my calculator. You know that's the right answer. I want to be able, if you have questions on how to do it, so I'm going to go 2 times the pi symbol times 60 times 7 equals, that was not so hard. Everybody get it? Okay, that's all there is. That's coils. That wasn't so bad, was it? Did I kill you guys or what? You gonna be okay? Okay. You're gonna find out on Friday. So let's do this then. Edit. Clear. Nobody go, wait. Okay. That's all I got to say about that. What number was I on? 15. Capacitors. 15 capacitors. All right, so what is a capacitor? A capacitor is a device that stores electrons. And I love how my notes right here are put like an accumulator. That's what it says, like an electrical accumulator. Well, this is a point in time where I have to explain what a hydraulic accumulator is and then convert it over to electricity so that you now understand. But while I was standing here, I thought, wait a minute, there's a thing like a battery. A very crappy battery that only lasts for a very short period of time, seconds or less. And shoot, I have a battery in my capacitor in my car. I could have brought that in, charged it up, and let you see it go snap. Capacitors can get you. They bite, and they bite hard. My air conditioner went out on my house a few days ago, week or two ago. It was really hot. Being the cheap guy that I am, and I always, when you call somebody to watch how they do stuff, you figure it out. And I noticed that whenever your air conditioner goes out, it's always the same part. It's a capacitor. and they charge you what, 150, 200 bucks to come out and do a service call. You know what a capacitor is on Craigslist on Amazon.com? How much? Like $5. So I ordered a $5 capacitor, and you know, while it's on order, I took the old one out and I brought it down here. We have a capacitor tester that you guys will play with the next few weeks. And I charged that thing up, and thought, well, I better discharge it. I turned around, there's a piece of steel right there, and man, when I put that on there, it went kapow! And it really held a charge. Interesting though, it was still bad. It was, because I did some other tests on it, and it passed the first few tests, which, and it, you know, if you watch, you know, on my YouTube certified heating and air conditioning, tell you how to check it with an ohm meter. I checked all that stuff, did everything according to YouTube. It checked out perfect. Brought it down here, checked it with my capacitor tester. Failed. Absolutely failed. Bought a new one, $5, put it in. Air conditioner never ran so well since we've owned the house. Heck. So here I've got a capacitor, which if you're watching at home, you can't see.
Big fast.
And let's see.
Home warranty though.
No, that's crap. All right. I've done this before and melted some wires, so let's just see how bad this goes.
Fireworks.
Yes, this part of the program is called Making Fire with Kevin.
Don't try this at home part.
He's touching it.
Well, yeah, because it'll
It'll
work for a minute. Well, what happened when it worked for a minute is what you actually saw was the electron, because this is DC. You saw the electrons flowing through this circuit into the capacitor, charging the capacitor. That's how long it took to charge it. So, then I can disconnect it and turn it the other way,
See some smoke.
and now you can see it kind of going down. So again, this is charging up. Hello?
Switch the other way.
I should. Charging up, charging.
Charged.
Stop. Charged up. Discharge. And by the way, that is a 0.025 farad capacitor. 0.025. That thing's large. So it's just like a battery. It doesn't last a long time, but it has a lot of very useful features to it. It consists of two plates or conductors. They don't have to be plates, but conductors that can hold an electrical charge. And are separated by an insulator. Which reminds me. I'm thinking about it, I'm like, oh, I have one of those. Here we go, here's a capacitor. So, there's your plate. Now this is a very long plate, and it's just wrapped, and here's your insulating material. So that's all that's in there. So have one plate and the other plate, and some insulating material that's going to charge all that up. And that's really all that's happening right there.
It went pop?
Huh?
It went pop?
Do it pop?
Did this one go pop?
Some stuff I inherited into my office in this condition. It looks like somebody purposely cut it open so you can see what it looks like, which is what mechanics do. We take things apart and, that's how it works. I'm going to need a new one. Let's see. Yeah.
So what's the insulating material? It looks like paper.
It is.
It looks like tissue paper.
No, it is. It's just tissue paper. Will it catch on fire?
Yeah, like wouldn't it catch on fire with the heat?
No, it's not really supposed to make heat in there. There's no resistance.
Okay.
So if you have resistance, you have heat. And it's just, no. Or maybe it's fire retardant paper.
I say if it was sealed, it can have fire.
Anybody got a lighter?
Oxygen, right?
Yeah, we should start on fire. Okay. See, the ability of a capacitor, the ability of a capacitor capacitor to store electricity. Electricity is known as capacitance. Known as capacitance, and is measured in farads. Farads with the F, because it's named after Michael Faraday. So 1 farad is actually a pretty large number. 1 farad, 1F, we'll spell it. 1 farad is a very large unit of measure. One farad can store 1 coulomb. Anybody remember how much a coulomb is? I remember it being as 2 pi, so 6.28 times 10, I think it's to 18, yes, to the 18th power. So that many electrons. Oops, that many electrons at 1 volt. So often represented as picofarads, which is 1 times 10 to the negative 12. So it'd be very common to see something measured in picofarad, because you can see that one is gigantic, and it's what, 25 microfarads? So you get one that's, one in a Magneto is an inch tall by thinner than a dime, or not thinner, but okay, capacitance. Capacitance of a capacitor. Depends on 3 items.
I'm a little confused still with the often represented as
Picofarads.
Oh, picofarads.
Yeah, picofarads. Which is just to say that we often are measuring, I shouldn't say represented, but you're just usually down in the picofarad range. So if you do a math problem, or you do one of these problems, you come up with something that's like 18 farads, you probably made a mistake. Okay, what are these 3 things? 1, area of plates. Area of plates. In other words, how much surface area is there in the plates in the capacitor? Obviously, the bigger the plates, the more electrons you're going to get. So, bigger plates is more storage. Thickness of the dielectric. Thickness of dielectric. Remember, dielectric is just a fancy word for an insulator, because the closer the plates, the more electrons are attracted. To the opposite plate.
Dielectric is the
Insulator.
So why do they say dielectric grease? That's like, it's an insulating grease. I thought you
Yeah.
put on terminals.
Yeah.
But how would it make contact? You put it on the terminals.
Well, I don't think you put it on, then put it together. You put it together, then put.
Oh.
Pushes
Oh.
it out of the way.
I thought you put it on first. No wonder.
Well, there's my problem. material. So what are my dielectric materials? Well, common material includes air, glass, ceramic, plastics, etc. Glass, ceramic. I could say paper, because it's right there, and other stuff. Air is the standard, with a dielectric constant of 1. And there is a thing called dielectric strength. That's the ability of the dielectric to resist breakdown, known as leakage. Hate it when I get leakage. Let me see. Dielectric strength. So when you get into magnetos, I'll have you testing capacitors. And one of the things on the machine is you can actually test the leakage. And so that's what you're doing, is how many electrons are making it past your dielectric material. So dielectric strength, and that is the ability of the dielectric to resist breakdown.
Okay, but what does that say there? Air is a standard with a dielectric what?
Constant of 1.
Oh, constant. Okay.
What are you doing way up there? We're down here.
I kept trying to figure out what that was. I kept going up the compound.
Breakdown.
You're welcome, everybody.
The working voltage of a capacitor.
Why did they have to change the word dielectric? Why couldn't we just keep saying insulator?
Well, then other people would know what we're talking about, and then we can,
I don't even know what we're talking about. Like, I just don't get it.
So you can charge more.
Yeah, I guess.
That's right. Tell people the spark tube is broken. Working voltage of a capacitor.
But there's no difference between dielectric and an insulator, or is there like?
I'm using it interchangeably.
Okay, I just wanted to make sure that.
Yeah. I'm sure somebody would tell me that's not right, but
I'm going with you.
Harry, you got any comments?
Nope.
Okay. You're just an idiot. I'm just sitting here and saying nothing. So, working capacitor of a working voltage of a capacitor. I think this is on one of the test questions, either mine or Q&A. Is the, now I got your attention, is the highest voltage that can steadily it's in the Q&A, steadily be applied to a capacitor without dielectric breaking down. Well, if I get a little tiny capacitor and I decide that I'm going to put 18,000 volts against it, what do you think the dielectric is going to do? Just starts to arc right through it. And then it's not so good anymore. And of course, this is dependent on the type, and thickness of dielectric, and thickness of the dielectric. And here's your answer. Working voltage should be 50% higher than the highest voltage applied. Than the highest voltage applied. Example. What if we had a 120 volt system? What would the working voltage of my capacitor, what should it be?
180.
How do you get that?
120 divided by, well, 120 divided by 2.
Okay, well I did times 150%.
Okay, that works.
All right, good. Equals 180 volt working voltage. All right, let's talk about capacitors. I just messed that all up. C-A-P-A-C-I-T-O-R, capacitor in DC circuits. All right, so when you put a capacitor in a DC circuit, something like this, like I have right here, and the symbol for capacitor is something like that, and when I do that, what happens, the electrons, at first, they see a wide open path, no resistance, this is the way to go. Everybody come, follow me! And all the electrons follow the leader, and they all run in here, and they come across here, and they start filling up this plate. They fill it, fill it, fill it, fill it. By the time it's all full up, it's like, whoa, hey, wait a minute. There's nowhere to go. And so in this particular case, if I have a large enough capacitor, what you see is as these electrons are filling up this plate, you will see this plate over here then is expelling is opposite of attract is repelling. There we go, repelling electrons through here, and you'll see that light up while it's repelling all the electrons on this plate right here. Now, as soon as this plate over to the right fills up, all the electrons stop flowing. So really, and you can look at this, it's represented, I see an open circuit. There is no path. That is truth. There is no path. DC circuits really see a capacitor put in series as a open. No electricity will flow. It will for a short period of time. If you have a very large capacitor, that's all you're going to get, and then it just stops because it's dark. Is that what you said? No. Charged. Okay, charged. It's open. It's an open circuit. Now, if I change this around a little bit, that was too much. Calm down. Change this around a little bit, and I guess we're going to use red right now. And I have a light here, and I put a capacitor here. What happens? Light's just going to keep on going until the battery runs dead. Why? Because this in fact is an open, but so what? It's not open here, so all the electrons are going to go this way. Now, the reason you'll see this a lot in DC circuits where they'll actually put a capacitor in parallel like this. And what that is doing is, and this is why we use the word accumulator instead of a battery, because it makes more sense if you've had hydraulics. And an accumulator, it's a large tank with a rubber bladder in it with pressure or a spring behind it. And so it stores hydraulic fluid on top. And so if you suddenly turned on a hydraulic motor or something, or sorry, the hydraulic motor is running and you use some very large piece of hydraulic machinery, you would see the pressure just drop suddenly until the pump can start catch up with it. Okay, well, with this accumulator, it sees that that drop down in pressure and pushes a whole bunch of fluid up into the system suddenly with the spring or air pressure. to keep that constant. So that's why we say electric accumulator. So what this would do is if you had a sudden drop in voltage, this capacitor will fill it in and keep the voltage kind of the same. Same way if you had a sudden spike, then it could go that way too. So it's a little bit of a filter.
What would cause those spikes and drops?
Oh, a lot of things. Like just think about your car. You know, you're driving down the road, you pull on your headlights. Plug in your cigarette lighter. What else you got in your car? Got to charge your vapor.
I still use my car's cigarette lighter.
And we talked about airplanes don't have cigarette lighters, do they? They have cigar lighters because we're fancy. All right. So capacitor and DC circuits. Let me see. A capacitor in series will act as an open. Will act as an open. And a capacitor will charge. Capacitor will charge. And current will stop. And current will stop. A capacitor in parallel will act as a reservoir. Will act as a reservoir. Reservoir. And what do we do with that? Well, it can be used to smooth out choppy DC. That's where your DC line isn't very straight, but it's kind of going up and down all over the place. Two, can be used, not can be, it is, can be used to protect points, in a magneto and supply current for a short time. So I'm going to go up in number 2, protect points in a magneto. We're going to talk about magneto in, 2 weeks? But I'm going to come back up to this drawing right here with the red because it's in parallel. And what happens in a magneto is we're going to be generating electricity. So I'll just kind of make this a little simplistic so we don't have to get into magnetos just now. We'll say we have some sort of AC going through here. And instead of a light bulb, what we have is, trying to make this at least somewhat realistic. Well, let's make it very simple. We'll keep it simple. All right, so points are a switch that open and close with the camshaft. So this cam turns around and it opens these points. They open, close, open, close, open, close. And it's going to do some other stuff down on the circuit here, which is going to make a difference what's going on right here. So what's happening further on down the line is not important right now. But what happens is we're talking about a lot of voltage going through here in the terms of thousands of volts, very low amperage. But when you have a whole lot of volts, you can jump gaps with these volts, right? And so these points, it's just a switch that's vibrating very fast inside this magneto, making the circuit go on and off rapidly. And there's a lot of things you can do with that, not in magneto, but we'll talk about that next week. So anyway, so what happens is we have this very high voltage, right? And so now imagine, if you will, we have a lot of voltage going through here, and we're going to slow everything down so it's just going very slow. And I have my switched close. And let's say I've got 1,000 volts going through this switch right here. And what I need in a magneto is very fast, rapid opening. I can't have it kind of open. And by that I mean the switch starts to open, but the electrons have so much voltage that they're just jumping across the switch. And so the switch is like open, 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 the whole time just sparking across. And finally I get to here and it's like, okay, now it can't jump anymore. You follow what I'm saying? So I want it the very second that I just barely break them apart, I need it to be off right now, and it's critical in the magneto that that happens. So what you do is you put a capacitor here. Now that capacitor right now is uncharged, okay? So it's kind of just, not all charged up. And so the minute I start to open up this switch, what happens is it starts to get a little resistance here. Capacitor has none. So all of these electrons are going, whoa, wait a minute, not this way, everybody follow me. And they all kind of run around. So instead of going this way, they all change their direction, go this way. They come down, they start filling up these plates. Well, meanwhile, this switch is getting further and further and further open. And pretty much by the time the electrons realize that the plates are full and this wasn't the way to go, and they start yelling, hey, everybody back the other way, this is a trap. The switch is too far open for them to go that way. It's too late. Now the switch is wide open.
Now prevents it from jumping.
Prevents it from jumping and arcing. So the points will last longer because you don't get the arcing, and it provides that very fast collapse of what we're talking about. The field is what we're going to be talking about. But so that's how points in old style auto ignition, the Kettering ignition systems and stuff like that. That's why they have points.
I was about to ask you that.
Yeah.
That's how points in a distributor work.
It's exactly what they do.
So how come on the capacitor, how come the electron wouldn't already be charged if it was wired in parallel?
I know, because in a second, this is going to come down here, and now it all wants to come out of here and go back down that way. So I know, in my mind, I figured it's kind of like a neutral charge, and then not negative, but this is how it works in my mind. And so it's not fully charged, it's kind of like got this baseline, and then when you open the points, then it really charges up, instead of being completely charged all the time. I know what you're thinking. So, yeah.
So doesn't that actually push out the electrons on the other side? Like the capacitor?
Yeah, it will, but for a short period of time, that goes down to ground anyway, so it's like, doesn't matter. All right. It's very regular. So, let me see. Capacitor, see. Let's see, we have so much. If a capacitor is connected in series and voltage is applied, current would flow at a maximum until the capacitor is charged. The point is charged.
Are we going to get shocked with magnetos in this class?
What?
Said, are we going to get shocked with magnetos?
Yes. Not as much as I got you guys last class. Okay, so how long, hopefully I won't be sorry for what I just cut out, but how long does it take, so it took a while for that to charge up, right? Took a while for it to discharge. Does it take to charge / discharge a capacitor?
5 time things.
Wow! It takes 5 time constants. Why 5? Because it's 63.2%, if I'm not mistaken. So it's exactly the same thing as an inductor. A little bit of a different formula. It's T equals R times C. Takes 5 time constants. All right. Well, here's the part that kind of hurts a little bit. All right. Capacitance in AC circuits. All right, well, a little bit ago, I drew this. The other day, I drew something that looked like this. And I said, and I showed you that when I connect it, it will light, this light's going to go on for just a short period of time as it charges up. And then when I disconnect it, it will light for a very short period of time. Otherwise, this sees this, the capacitor as a open or closed. What? Open. Okay. But now we're going to change this because that was DC. So now we're going to say, well, what happens when we have AC? So we have AC in there. Well, in an AC circuit, it does not see it as an open. It flows right through it. So the light is going to be shining at all times. Now, when I say it flows right through it, that is completely false. It doesn't flow through it. So what's happening is just because it's reversing constantly, it's constantly charging and discharging, charging and discharging. So, for a brief second there, not even a whole second, all the electrons are flowing this way, and they're going to start filling up this plate just like we talked about, and they're going to repel all the ones on this plate, so it's going to flow this way, and it's going to go through the light, and it's going to be a complete path. But right about the time the capacitor is completely charged up and ready to give up, what happens? Reverse polarity. So now all the electrons are going to start going this way, and the light keeps going. And so it goes around, and it starts filling up this plate that was empty, and it repels all the ones this way and goes around. So in an AC circuit, it does not see that as an open. It just sees it as a wire, sort of. Huh? Can it make a jump? You put enough voltage on anything, it'll jump it. That's a nice thing. Just how much? Okay, because AC's, so I can write that. So I'm just going to tell you guys, every time you do this, it goes through my mind. So I might as well share with you what I'm laughing about up here that you can't see. So years and years ago, one of the classes, in every class has its own little personality, own little jokes. And I very much love that. But one class, because I wasn't tenured yet, and I was evaluated every single year. And so what happens, and you're going to see it now because we all have to be every so many years, and it's cycled. But anyway, what happens is I will leave the room, and another instructor will come in, and they're going to say, hi, here to talk to you about Kevin, and show me on this doll where he's touched you. And see, that's what's going to get me in trouble. And so they're gonna anyway, so there was this it became this joke, because then they hand out this thing and you fill out this evaluation on me, right? And so there was somebody over in this area, and every time I would say something like that, he would go, and I'm like, what are you doing? He goes, I'm writing that down. It was a joke. So then the whole class, I would say something like that, and the whole class would at one point go and look up at me. So when I talk to you like this, and I'm going to start writing, and every one of you goes just like that. So I'm like, what are they writing? How much trouble am I in? Well, it wasn't until that comment. So, but I mentioned I'm tenured, so I guess it's, I don't know. Okay, because AC is constantly changing, a capacitor will charge
It's doing this extremely fast, right?
Yeah, like about 60 times a second for right here. 400 times a second aircraft. See, a capacitor will charge and discharge constantly, making it appear, write nicer, M-A-K-I, making it appear as though current flows through it. Making it appear as though current flows through it. Flows through it. When in fact it does not. I'll write that. When in fact it does not. It does not flow through it. It just gives that appearance. All right, when voltage is applied, maximum current flows instantly. So it's like this, right? It's like getting into Disneyland with my kids. right? You guys been to Disneyland?
Terrifying.
You know, you kind of got on the kids, and we walk through the gates, and without any push, even the slightest little bit of, maybe a head nod or a wink, boom, there they go, right? So I guess capacitors are kind of like Disneyland or something to electrons. So at the slightest of encouragement at all, they are off and just gone. So there goes the current, off and gone. And here's voltage, the dad going, where'd everybody go? Don't worry about it. They'll be back in 1/60th of a second because I've got the wallet. So, so the electrons see this gigantic plate, right? I mean, look at you got a wire going into here. You just got this little tiny wire, right? And so, and it hooked up to this. But now I got plate on here that's going to go from me past the door this wide. That's like this huge wire. And so it's all this place for electrons to go. So then they're just going to take off and go. No encouragement whatsoever. Just as soon as there's the slightest bit of voltage, boom, they're gone. So that tells me that the current is going to lead the voltage. And that's why, because it's just so wide open, even the smallest of voltage, and the current is off, and it's flowing to the maximum. How much current goes? All of it. So let's see. So voltage supply maximum. This is because a capacitor plate easily takes a charge, which is a flow of electrons. So this is because the capacitor plate easily takes a charge. Which is flow of electrons, which is the flow of electrons. All right, max current happens as soon as the voltage moves off of 0. So max flow happens as soon as voltage moves off of 0. Then as electrons build up on the plates, the capacitor now starts to reject anybody else. Hey, the end is full. You need to go somewhere else. All you electrons that were the last one to get here, sorry, go away. So, well, I should write this one in. So in an AC waveform, forgot to write this, max current is at 0 degrees. Why? Because we're just at 0 degrees or 0.0001 degree, we moved off of 0, and it's going to start building right at that point. So as soon as it gets off that little 0, boom, there it happens. So 0 degrees, you have max flow. Well, where's peak voltage then? How many degrees? 90. So now we know that the voltage will lead the current by 90 degrees. So, Iceman. As electrons build up, the capacitor opposes. The capacitor. We should just abbreviate CAP, because then we would save time in SeaWorld. Where was I? Electrons build. The capacitor opposes additional flow. So eventually, if it wasn't AC, well then it's DC, and then it just would stop additional flow. Also, I could see that happening if you had a very, very long wave. Your frequency was super, super low, and it would probably charge up and just kind of stay there waiting for it to reverse and go the other way. So So this point was, I'm not sure, there is then zero flow, no flow, when voltage is at max. Because it's already charged up. Now this is of course assuming that you don't have anything else in the circuit, you just have this capacitor sitting there. And then we said this, therefore, you don't have to write the therefore, because I'm not going to spell it right anyway. Therefore, current leads voltage by 90 degrees. We'll make this one 6. Cut some of this out. I'm cutting this part out. So when applied voltage moves through 90 degrees and starts decreasing, voltage moves through 90, starts coming down, starts decreasing, the capacitor discharges, keeping the current flowing. We already talked about that. As voltage passes through 180, the capacitor, which is fully discharged, allows current to flow and receives a charge. All right, the amount of current, oops, time for break, huh? Well, let's finish this point. The amount of current that a capacitor allows to flow is dependent upon the capacitance and the capacitance of the capacitor and frequency. The amount of current that a capacitor allows to flow is dependent on the capacitance of the capacitor. I won't write that part. On the capacitance of the capacitor and frequency. All right, and we'll come back to this in a few minutes.